Hello, everyone. First of all, thank you for coming to the talk. My work won't be possible without my students and postdocs, so you see like a large list of names. But mostly these are postdocs and students who basically contributed to a lot of work that we've been doing together in the group. For those who don't know what Flatiron Institute is, it's a new institute funded 100% by Simons Foundation. It has an endowment of, I think the institute has an endowment of like $1.2 billion. And it has 4 centers. The first one is Center for Computational Astrophysics, which is where I am at. There's Center for Computational Biology, Computational Mathematics, and which is basically half machine learning, half numerical methods. And the other one is Computational Quantum System. And there will be a new one called Computational Neuroscience. So all of us are applying new methods or developing new methods to advanced science in different ways. And I moved, for those of you who don't know, I was at Carnegie Mellon as a faculty, then moved to Berkeley, and recently moved to Flatiron with a joint position at Princeton. So without further ado, my student who just graduated, Shirley Ho, who just went to Plus AI, is doing a self-driving cars now. Ying Li, who also did a lot of work here, is at Flatiron Institute coming from Berkeley. Miles Kramer is a second-year graduate student in Princeton. I just want to highlight those few names because you will hear about their work later on. All right? So the universe as we know it, for those who don't do, basically cosmology, which is what I do like every day, in the 1900s, we think everything's a baryons. Baryons are stuff that like we can just touch and hear and heard about. Protons, quarks, neutrons, all that stuff is baryons. But baryons, since they describe everything, right, these interact through only gravity, but also through hydrodynamics and electromagnetically. To model baryons correctly, we require modeling hydrodynamics, magnetic hydrodynamics, gravity, all that stuff together. But in 1970s, we discovered like 85% of it is called dark matter. For those who never heard of this word, you can see references in Avengers. No, people don't know what Avengers is also. Marvel Comics. Okay, good. This was also mentioned in Marvel Comics. I think this was the dark matter that entered. It was like somehow got into Natalie Portman and it has some basic effects I don't understand. But that was not that. Nobody really understands what dark matter is. But our best guess right now is that they are cold, which means they're not moving very fast, not temperature-wise in the sense that we kind of casually call cold. It's massive and only interacts through gravity. And the reason we know there's dark matter, there are many reasons, but one of them is that if you look at this stretched out galaxy image, it's basically a strongly lensed galaxy image. The galaxy in the back is just little, ellipses, but it got basically the light coming from the galaxy got stretched into this ring. It's called an Einstein ring. And there's a lot more matter if you look at how much it's getting stretched by the space-time, these light photons coming to us. And you can guess how much matter there is. It's way more than the amount of matter that will be predicted by this bright galaxy of stars that you can observe. So we think there's some extra matter there. And given that you're in Switzerland, Geneva area, CERN is looking for the dark matter candidate, which is very close to here. So hopefully you know about dark matter soon. And then the universe as we know it now has been changing. We have dark energy being 68%, dark matter being 27%, and baryons being 5%. So the stuff we all know and love is 5%, unless you're a cosmologist. And that's sort of the blank space that we know about dark energy. We know very little about it, except that we named this term to describe our ignorance in the face of the fact that the universe is accelerating its expansion without any good reasons, or if you believe Einstein is incorrect. If you believe Einstein is incorrect, then you have other explanations you can do, and people do try to modify Einstein's theory of gravity. So that's another way you can do it. Or you think there's something called dark energy that nobody knows. And another reference to Marvel Comics, for those who are not into Marvel Comics, would be like, what is this? The first scene of the Avenger movie, there's like this collapse of this center that's like everything exploded because it's dark energy thing. It's called Joint Dark Energy Mission. There was a mission that was designed to detect what dark energy is from NASA that didn't actually happen, but later on become something called WFIRST. So for people who work with the space industry in NASA or ESA, you might have heard of this. Enough references to movies that people don't watch apparently in this land. Okay, here you go. So the nature of dark matter or the nature of dark energy. Oh, by the way, feel free to ask questions in the middle, although maybe the old coordinators won't let me. Because it's okay to ask questions. I designed the talk to be a bit shorter than it should be, So you can ask questions in the middle if you like, just like raise your hands. I would argue that the nature of dark matter and dark energy, arguably two most interesting questions in physics that are open, but probably two most expensive ones. Maybe not the two most interesting ones by your count, but I think probably two most expensive ones in physics. The Large Hadron Collider cost billions of dollars per year or something like this. The Euclid telescope is like €1 billion in the year $2,000. So I don't know exactly what it costs now, but it is a ESA-led mission that's, I'm also part of the team. And we're very excited to analyze some of the data coming from hopefully Euclid very soon. And this is a movie that you cannot see very well because of the lighting. It's all the galaxies you see when you zoom out from Earth. They're real galaxies, they're not fake. These are actually observed galaxies by the Stone Digital Sky Survey, which is on top of a mountain in New Mexico, not in Mexico, and in Apache Point Observatory. The red dots are the red and dead galaxies, and the blue dots are the sort of like young, star-forming galaxies. And very soon you'll see these like purple, blue-ish dots very quickly. These are the quasars, the supermassive black holes that emit in certain ways. This is the larger structure of the universe that we kind of love. And for those, let me see if I can pause this. For those who don't do this for a living, do you know why we only see these slices? I will buy very expensive beer or coffee for those who get the questions right. Who's not a cosmologist? If you're a cosmologist, go ahead, try. Do you want to pick the person? Because I don't want to be. Raise your hands who wants to answer a question. I'll let her pick the. No, there's. Milky Way is a good one. So you want to avoid look at the Milky Way. Otherwise, you see a lot of stars. That's great. That's one answer. There's multiple reasons for it. So I need to buy multiple very expensive alcohol later on. Yes. Dust clouds, we don't actively try to avoid, but we try to avoid by avoiding Milky Way. So it's the same answer, but that's good too. More suggestions why we only see, the universe is homogeneous, right? It's not like that, obviously. But I'm telling you, this is an observed data set. More suggestions. Come on, you guys work on satellite data set. Looking on the ground, you should know. What was this? Oh, not this one, but it is a good guess. Yes, in the back. Maybe the sun is in the way? Yes, well, we don't observe during the daytime. That's a very good one. But that also relates to something else, which I think you can guess the next part. The hemisphere or the location where the telescope is? Exactly. This is what I'm looking for. We can't look through the Earth. So the telescope's on the ground, so this one. So I guess this is a fun part that the telescope I'm talking about in New Mexico, remember, is on ground. It can only look up during the nighttime. So I owe 1, 2, 3 beer or alcohol. It's very expensive. I guess that would cost like 1,000 francs or something. Okay, so great questions and great answers. So this is basically what we can't see. This is what we can't see is, for various reasons, but what we can see, you actually see the universe has this large-scale cosmic web. The blue dots I promised, these supermassive black holes are zooming through. And furthest away is the cosmic microwave background, the baby footprint of the universe since the Big Bang, in case people don't know about this. And those are hot and cold spots from the explosion of the universe at the beginning. Okay. And these are two scales, in some ways, as a function of time, since the birth of the universe. So. And you can see that the survey, as is already, has seen, halfway through the universe in time, which is pretty awesome, I would say. And we have to analyze this data set. How do we analyze this data set? In particular, we're going to analyze a data set that looks like this. Okay? So that's what we're going to do. So what we usually do, we take the distribution of the matter over here that looks like this cosmic web, this spider web shape, and we put it into something called this analysis routine that was generalized to some summary statistics of the universe. In this case, I'm going to concentrate on the matter field. We're not talking about the galaxies directly yet, but just the matter of the universe. And for different dark energy parameters. This is called W. It describes the dark energy in certain ways, how it evolves as a function of time, more or less. And actually, it is specific to a ratio from pressure to density for this parameter. And you can see that it gives different summary statistics, and you use that, you can constrain dark energy. So this is the bread and butter. I did, in like 5 minutes, explain to you how to do cosmological analysis to understand what dark energy is. Except, it doesn't take all the information, right? It takes a field that's highly non-Gaussian to something that's basically described by 40 numbers. So, and the experiment, like Euclid, is $1 billion experiment, and you got 40 numbers. It's a little bit huge compression in data. So we're trying to do something a little bit better than before. This is actually the question I asked, if we can do better than what we've done before, because that's what I got tenure for. And once I got tenure, I decided that we should do something crazy. And mind you, when I did this, nobody was doing machine learning in cosmology. Well, not many people, maybe like 3 people. So we wrote in an ICML paper, that was way back in the days where doing 3D convolution neural net, you have to write it yourself. So we took these different dark matter distributions that has different cosmological latent parameters of the universe, and we throw it into a neural net that apparently we didn't have a 3D conv net back then. This is way back. This is to tell you what happened really old. Throw all these cubes of dark matter, and you want to get at the cosmological latent parameters. See what happens. So we input n-body simulations with known latent parameters to train the conv net. We validate, and we test, and we basically know that, we only get these little cubes. By eyes, you cannot tell the differences between all these 3 cubes when they have very different cosmological latent parameters. So the red dots is what I got tenure for, which I was very unhappy when I saw this plot, because the blue crosses is what the ConvNet was doing. And this is sort of like our first plot that was actually published at ICML, but we later on got a lot better, because in ICML you only did it in like 2 months, so we have to rush. But you can see that it basically improves dramatically from what people usually do to what you can do, because you take all the information in from these little cubes of dark matter distribution, this matter distribution, to all these predictions, these crosses, then the red dots. So we thought, okay, you can in principle achieve high accuracies on these billion-dollar experiments by a factor of a few with just using a simple ConvNet, 3D ConvNet. So we thought that's something we should think about. So we put in dark matter gravity-only simulations simulated by the universe for trainings, validation, and test set. We want to test with the actual data set, obviously. Throw it into regression with neural net. You got these latent variables, which apparently cost billions of dollars. But what we wanted is a fully realistic simulated universe for training, validation, but we also accept the observed universe, because we only observe one universe. We can't simulate it. So how do we do that, right? We basically want to do a full realistic simulated universe with machine learning, which is what some of this I'm going to touch on today, but I won't be having time to explain the whole thing I'm going to do. A full theory prediction will become the fully realistic simulated universe. So that's the plan. So what I'm going to talk to you later is how to use deep learning to simulate the universe. And basically what we want to do is to simulate this. It is a fully, simulated universe with gravity, hydrodynamics, and magnetohydrodynamics. Right now it's probably describing you the temperature of all this gas. That's an exploding supernova there that makes it really hot in the surrounding. It's a very complex simulation. It takes 30 million CPU hours to run it once. So we might not want to run it so many times because you need to take, several thousand training sets. That could be quite expensive. Might be more expensive than building a telescope to try to do it so many times. So what do you want to do? We want to simulate, the dark matter simulations or the gas temperature and all the galaxy positions and the neutral hydrogen, all that stuff that we will observe in the universe without running these very expensive simulations. So that's the plan. So we want to simulate the universe super, super duper fast. When this one will take 1.8 million CPU seconds just to generate, this one takes 30 million CPU hours to generate. But I want to make a lot of these and a lot of these, like 10,000 each. Okay? So all things interact through gravity. It forms the backbone of the universe. And that's why we're going to try to do this one first. And we're going to model gravity interactions first because we're only the massive particles interacting gravitationally with dark energy included. And in the following part, I don't think we have enough time to go through this part of the talk, where we actually simulate the universe that would take 30 million CPU hours. We did it in 1 minute. So we encourage you to read that paper. It uses a Wasserstein GAN, for those who probably does GAN for fun. But I'm not going to touch on this. This one is more fun to talk about, also simpler to talk about, because it's using fairly simple architecture, and there's some surprising effects that came out of it that I will discuss with you guys. All right, but this is easier, because only 1.8 million seconds. This one's 30 million CPU hours to run. So that one is dramatic, speed up, while this one has an interesting property that I will show you soon. All right, so let's do that. We're going to try to simulate the dark matter evolution of the universe for 13.6 billion years, okay? So the input is something that we're analytical approximation of the universe, like approximately what theorists can write down paper and pencil. That takes no time for the input. The output would be the positions and velocity of all the particles evolved under gravity after 13.6 billion years, which is the age of the universe as we know it. Instead of using numerical simulations of Newton's law or general relativity, it doesn't matter at this scale. For all the particles with smart algorithms to run really, really fast. This is 40 years of work, so people have made it run really fast already at this point. We attempt to use machine learning to learn or interpolate from a large number of pre-run simulations. So when I say people are making it run really fast, it's 1.8 million CPU seconds for one simulation. So what we did is published recently in Proceedings of the National Academy of Sciences. We have the input, as I said, basically people can write down paper and pencil, the analytical approximation, when the outputs of the velocities and stuff. These are slices of the box. I'm not showing the 3D box, but what we predict is all in 3D. The machine learning model is super simple. People already mentioned earlier, it's a UNet, but for the physicists, it's interesting to look at it because you want the same input and output sizes. And because of the large-scale predictions of the analytical approximation is correct. The large-scale physics is correct, and we want to keep those. That's why the concatenation layers is needed to pass the large-scale correlations in, because we want to learn the small scales. So for those who do a little bit of physics, what the analytical approximation can do is that things fall in, they keep falling in, but it passes through each other. It does not interact. What the numerical simulations do is things come in spiral and interact and coagulate into a clump. So that's the part the machine learning is learning, okay? All right, so we have 8,000 pairs of analytical and simulation 3D boxes for training. Each one of them is the size of the survey you saw earlier with the Sloan Digital Sky survey. That's about the same size. And we use the UNet, and also its translation invariance for the universe. It makes a lot of sense. And we also put in something called periodic boundary conditions for this particular simulations, otherwise it won't work, by the way. And everything is public in our paper. So all the codes and actually even the data set is public. And we want to make the predictions. So let's see how well we did. This is already a money plot. We want to show the errors in the displacement field predicted by the benchmark model, basically what people use, including me, before machine learning, to model the universe when we analyze the data set. In our machine learning model, what's the displacement field for people who don't do physics is the difference between the current position to the initial positions of the particles. Okay, it's not too bad. That's the error bar. The error is in something called the megaparsec over h. So for the people who are very Star Trek fan, you probably heard of parsec. It's not velocity, it is a distance. So 1 parsec is a distance. It's about 3 light years. So this is, 5 is the maximum. 5 times 3 is 15 million light years. That's basically the scale here. And there's some errors that's really large. You can see that they will hit 5 megaparsec. So it's really big error bar for the benchmark that people have been using before. Actually still using right now, as a matter of fact, in the cosmology community. And here's our machine learning model prediction errors. And you can see that it's basically about, the maximum error here is 0.7 megaparsec. The maximum error here is 7 megaparsec. So it's about a factor of 10 improvement. And we also check something very statistical for physicists. I know a lot of you guys are not doing physics here, but I'm going to quickly summarize this. We're going to check very quantitatively what cosmologists care about. This is the average Pau spectrum. Pau spectrum is just the Fourier transform of the correlation function of the box of 1,000 simulations, the ratio to the true Pau spectrum, and the cross-correlation coefficients, which cares about the phase correlations of the two boxes that you're comparing. The 1,000 simulations are predicted 30 seconds, which means everyone is in 0.03 seconds. And one training simulation takes 1.8 million seconds to run. And it's very funny, cosmologists, we like to plot the large scales this side, small scale this side, okay? And now you look, you're like, okay, this is very confusing, I understand. And the green line is what you want to concentrate on, is the truth, that's the green line. And you want to see where the orange line is, which is wild prediction. And basically you can't see it, because it's right underneath the green line. The benchmark model is the blue line, which is not so bad. And if I divide both the orange line, which is our predictions, and the benchmark model by the green line, that's what you get. The orange line is basically barely peeking out at scales that actually people can't predict correctly before by quite a bit. This is what we used to use. Actually, we still use regularly. And we are at percent level at these scales when they talk about 50% wrong. And we're 60 million times faster than the previous simulation generations. So we thought that was pretty cool. But we want to do even more. We want to test something that's crazy. This is the part, if you're going to listen, I think that's where I'm going to listen, which is when I input different cosmological parameters, which means we are trying to test with things that are of different latent variables that are different from the training set. The model is trained. We're not going to change the model. It's fixed. We're not changing it into hyperparameters. We're not retraining anything. But we're going to input something with different dark matter density parameter, which means the universe looks very different. Before, it's usually 30% dark matter. At the beginning of the talk, we talked about it. Now, it's going to be 10% or 50% dark matter. We even tested 90% dark matter and see what happens. Can the learned model extrapolate outside the training set very specifically? I mean, outside the distribution of the training set, not even outside just the training set itself, and that do not have the same latent parameters, completely not the same latent parameters. So let's check this out. We made the same plot, and here this time is even more confusing because I'm going to show you the truth with the solid line. Long dashed line is our prediction, and short dashed line is a state-of-the-art benchmark with the same plot. And for the different latent parameters, so omega matters 0.3 is our latent variables that we have in our training set. So for this orange, is what the training set is trained for. Of course it's doing well because the long dashed line is right underneath the solid line. Okay, but it works even for omega matters 0.5, which means a very different universe, 50% dark matter, and when it's 10% dark matter. While the benchmark model for both the 50% and the 30% universe all failed, pretty much. And you can see it pretty easily here. This is the benchmark model, it's a short dashed line. And the long dashed line, it basically works still quite perfectly, even for something completely different from our training set. So this is zero-shot learning. We did not know it's called zero-shot learning when we actually did it. So we just thought, oh, this is cool, this is very weird. And it works also for, this is the error Pau spectrum. And you can see that the long dashed line is doing really well compared to the benchmark, except here. And here is interesting because why is it doing like this? We still don't know. For omega matters 0.1, which means only 10% dark matter universe, the benchmark model actually performs well at the larger scales. It makes sense it performs well in the large scales, but it doesn't make sense why the model didn't actually quite learn in the larger scales. That's the only thing. So what the heck happened? The model generalized significantly outside the training set, not just the specific instances, but the distribution itself. We did not explicitly use any transfer learning like people talked about earlier or meta-learning. Maybe there's an overlap between these universes in terms of information directly. Or maybe there's some kind of structure in a universe that generalization, extrapolation by the network is easy, quote, quote. Can we explain or interpret this generalization? Or maybe I can finally get famous. That's what I was most happy about. My possible climb to fame, that's what I thought I would get famous for. There are two very important people. The first one is important to me, because my husband. The one is important to some people who are climbers. He's an astronaut who recently climbed El Capitan without ropes, for those who watch the movie Free Solo. Maybe if you don't get references for movies in this crowd, I just realized. Anyway, he climbed many, many thousand feet without rope by himself. And it was shot into a documentary called Free Solo for those who haven't seen it. And they were climbing together. I was taking pictures. I thought, hey, this is my climb to fame. This is like 4 or 5 years ago. So my husband's a crazy climber. And I thought, now maybe it's not climb to fame with climbing, but actually understanding machine learning, or compressing learned model into physical laws, or discovering new laws of nature. So this part, I will encourage you to read a paper published by my students, Miles Kramer at NERPS recently. And we are able to use graphical neural net to look at a bunch of observed data sets and derive the physical law really, really fast by using inductive bias in physics, basically knowing that it is a 3-dimensional physical law, and you limit the message passing in the graph network and made it super fast. So, and that's it, I guess. Thank you so much.